This week we're talking about soil physical properties. So this is, you'll see this pie chart around. This is your typical or ideal soil. So 50% is going to be solids, and that would be 45% mineral, 5% organic matter. And then 50% would be pore space, which may be filled with air and or water. And this is an ideal soil, which is pretty rare actually. The three particles that we're going to talk about are sand, silt, and clay. I have gravel here so you can kind of see the different sizing of materials you may find in soil. So sand doesn't stay together, it doesn't aggregate. I'll talk about what that means in a minute. It's made of quartz, which is most resistant to weathering. It's very slow to break down, and it contributes little to plant nutrition. Silt is what you're going to see on lake bottoms and along riverbeds. It's very small, can't see it with the naked eye. It's very fine, and if you were to feel it, it feels like flour. Clay are the smallest mineral particles in the soil. It's the most active portion of the soil minerals. Chemical reactions occur at their surface. Absorption and release of plant nutrients happen here, and I'll talk about what absorption is very shortly. Clay particles have about 1,000 times as much external surface area as the particles in an equal weight of sand. So we'll be talking about porosity next week, but think about it, with all that surface area, clay actually has more porosity than sand does, but that doesn't mean it drains well. Okay, here's adsorption versus absorption, and adsorption is when molecules adhere to the surface, and absorption is when they're drawn into the surface. So here's the relative size of the particles again. Sand provides good drainage. It does not hold moisture or nutrients well, though. Silt holds moisture fairly well. It holds small amounts of nutrients, and clay holds nutrients and water and soil but does not drain well. So here's the soil texture triangle. This gives you an idea of where your soil types lay as far as what the percentage of sand, silt, and clay are in the soil. Loamy soil has an equal influence from sand, silt, and clay, and I'll show you what that looks like. The thing to keep in mind is because clay has such small pores, it has the greatest influence on soil texture. So loam is going to be equal influence, but not equal amounts. So just to get an idea of the sizes of sand versus clay, it's quite a bit larger. So soil texture is really important property of the soil. It greatly affects land use and management. It affects how much water and nutrients that a soil can hold and supply to plants. And other physical properties such as structure and movement in air and water through the soil are affected by this texture. Soil texture is affected by the parent material once it's been modified by weathering and soil forming processes. So texture really is a relatively permanent physical property under natural conditions, and it's not practical to try to change it. Sometimes you will see people add sand to an already sandy soil for like soccer fields because it helps with drainage and allows for long roots on the grass so it can hold up to the wear and tear. The thing you have to look out for though is if you add sand into clay soils, because there are very tiny pore spaces in clay soil and those will be filled up by the sand, and so it effectively makes concrete. Much better to add organic material if you need to do something about the structure of the soil. So you can send in your soils to be tested in a lab, but we are going to be doing it in our lab activities, and it's pretty pretty close. You can get it pretty close. So here's the texture by feel flow chart. We'll definitely be doing this. It's kind of a process of elimination, and I'll be sharing a video for those who are not going to be in class to do this. So the soil texture classes are based on what the proportions are of sand, silt, and clay, and there are 12 different soil textural classes. We use the texture triangle to determine this textural class. So you have the units on each side of the triangle, and then everything's going to add up to 100%. So here we have 42% sand, 35% silt, and 23% clay. So we are going to be using these triangles in our lab. So what we're going to do is we're going to look at, let's choose the percent silt side. So go on that side, and then you're going to draw a line from 35% down towards the base of the triangle, angling it at the base of the triangle. Then you're going to go over to the sand. You're going to find 45%, draw a line up that way, and then 23% across, and they meet in loam. So that's loamy soil, and you can see, as I said, 23% clay compared to 42% sand. That's loam, and it has a very big influence. You can see that. So when you're determining soil texture, you're not looking at organic matter. It's not considered when you're determining soil texture. And if you want a really precise analysis of soil texture, that requires organic matter being removed. And the jar test is another thing we're going to do in lab. That helps. Otherwise, you would have to have the lab burn it off. That's the way they do it. And but usually the organic matter floats to the top. The jar test is with water, salt, and water. So I'll be sharing that information with you. Soil structure is the arrangement of aggregates or beds in a soil, and it creates different size pores. It can retain adequate water. It can allow for drainage and excess water. And the forces that cause soil particles to bond to each other are biological, chemical, and physical. So soil microorganisms excrete substances. They act as cement agents. They bind the soil particles together. Fungi extend into the soil and tie soil particles together. Roots also excrete sugars into the soil that help bind them together. And there may be naturally attracted particles attracted through electrostatic forces. And we're going to talk much more about soil organic matter, but just to let you know the different ways that soil organic matter affect structure of soil. Physically, it improves aggregation. It improves water holding capacity. Chemically, it increases nutrient availability, nitrogen and phosphorus cycling, solubility. It increases CEC, which is cation exchange capacity, and we will talk about that. Organic matter, as I mentioned, clay is very chemically active. Organic matter is even more active than clay particles, so it's important to have organic matter in your soil. It can also help buffer against pH changes. And biologically, it increases the microbial diversity. It helps with nitrogen fixation. We'll talk about that. Phosphorus availability through mycorrhizal fungi. And it can also increase pathogen suppression. So here's what soil structure looks like. So soil aggregate, so we've got our soil particle, and it's aggregated with organic matter. There's probably some hyphae in there, fertilizer, etc. So a soil aggregate is that singular unit. Soil structure is a collection of aggregates. And here's a little graphic here to show you that you've got your dispersed state of soil particles, and then the byproducts from the microorganisms glue the particles together, and then there's your aggregated state. You need organic matter in your soil to have products to be broken down and giving off that glue. Okay, here's some typical soil structures from various types of soil. Granular, that would be the dark surface soil. Hopefully you've got some of that in your garden. Blocky for clay-enriched subsoil. Prismatic for subsoils under grasslands. Columnar, these are sodium-affected subsoils. Grasslands is more arid conditions. Platy would be alluviated subsoil. This is leached of clay, minerals, and organic matter. Soil structure may be destroyed by compaction or excessive tillage, and tillages of wet soils can damage soil structure. So if you need to till your soil, wait until it's not so wet later on in the spring. And if you lose organic matter, that certainly can help weaken the soil structure. So on the left here, we've got no-till soil, and then on the right, you've got tilled continuously. And you can see some really beautiful aggregation there on the left. And compacted soil is a huge part of the problem with our soils, certainly in new construction and anything that's had a lot of foot traffic, etc. Normal soil or ideal soil, the water and the air are going to go right through there, but compacted soil, it may not make it in. And if it does make it in, it may not leave. So compaction impedes root growth. It limits the amount of soil explored by the roots. It can decrease the plant's ability to take up nutrients and water. And in dry years, it can lead to stunted, drought-stressed plants. The roots are not going anywhere. They're just staying there, and they're not growing prolifically and able to gather more water. So here's compacted soil on the right here. So we're going to talk more and more about soil compaction, but it reduces pore space, it increases bulk density, which we will be talking about, root growth inhibition, low water holding capacity, reduced water infiltration and percolation, reduced aeration and anaerobic conditions, and increased erosion.